The word laser is actually an acronym and stands for Light Amplification by Stimulated Emission of Radiation. Lasers can be made to emit any sort of electromagnetic radiation or light needed, from UV to visible light to infrared, and all other types. Did you know that the first lasers were microwave lasers and called masers? I didn't think so. To get a laser diode chip to laze or emit laser light, current is pumped into a laser cavity. A laser cavity is where the material that will laze is located. This is known as the gain medium. There are many designs for a laser cavity, but the simplest and most common is the Fabry-Perot design. From the light produced in the gain medium, most remains in the cavity to sustain the lasing, and a small proportion of it is let out. This means that the light is highly collaminated, or will travel in the same direction. How is this light produced in the gain medium? First, we have spontaneous emissions occurring that produces photons. These photons are produced from electrons falling from the excited state to their ground state in the medium, releasing their excess energy as photons. Photons of frequencies that are harmonics of the fundamental frequency of the laser cavity will continuously oscillate along the cavity, and photons of other frequencies won't be sustained. If a photon with a set value of energy comes along to an electron in the excited state, the photon will cause the electron to drop down and emit a photon of the same energy as the initial photon. This process will continue, with more photons of the same energy produced like an avalanche. This is when we can say the material is lasing. This graph shows the current against voltage and power of a single contact diode laser. The red line is the power against current of the laser. We can see here clearly that there is a sharp increase of the slope of the red line. The current where this sharp increase in power occurs is known as the threshold current, and it is where the laser begins emitting laser emissions. Before the threshold current, there is only spontaneous emissions from the laser. This is the same way a LED emits light. This light is incoherent, which means the light emitted is non-phase. This means that the light waves are not in sync with each other. The peaks and troughs of different waves do not move together. But at the threshold current, there is amplified stimulated emissions that we would call lasing. After threshold, the light becomes coherent and monochromatic. Coherent means that the light waves are in phase and travel in the same direction. We can see how this would look by looking at these oscillating strings all hanging from the same stick. Notice how the peak and troughs of the ribbons are in sync and the wavelengths are all of the same length roughly. While this video isn't very steady, these strings are a good visual aid for understanding coherency. This is called being in phase. Monochromatic means only one frequency of light is emitted. Here we can see a graph of frequency against power of a single mode or single frequency laser. This kind of graph is also referred to as the spectrum of a laser. This peak in power is not as instantaneous as expected from theory due to thermal broadening of the energy levels. The frequency of the light emitted can be found by finding the difference in the energy levels between the excited state and the ground state of the electron in the gain medium in this equation, where F is the value of the frequency of the light, H is a constant known as Planck's constant, and delta E is the difference of the energy levels. However, in diode lasers, this isn't always the case. They can be observed to laser multiple frequencies. These lasers are called multimode. This is due to the fact that since diode lasers are very small, usually around a few microns in length, their cavities can support multiple resonant frequencies with ease. These other modes are often unwanted and can be suppressed using several different methods, including using a filter. The line width of a laser is the full width half maximum of the frequency of a single mode laser. There are many methods to measure this accurately using heterodyne and homodyne methods, but for narrow line width lasers, it is especially challenging to measure this. Thank you for watching.